Welcome back to this series on graph theory. Last time we made the basic definitions we need to describe paths and cycles in graphs. And today we're going to look at the length of paths and cycles in a given graph and how these lengths relate to other parameters that we've seen so far. The first question we'll try to answer is, how long can we expect the paths and cycles in our graph to be? For this question, we can imagine that we're given some graph G, and we don't necessarily know what the exact structure of G is, but we might have some idea of some of the parameters that G has. If we now want to find a long path in G, we could proceed as follows. So we could start at any arbitrary vertex. Let's call it x0, and then we could try to extend a path from x0 as far as possible. In this case, we would have to look at the neighborhood of x0 and then choose some vertex in that neighborhood and extend the path to that vertex. So this would be, say, x1. We now do the same thing for x1. We look at its neighborhood, and then we would choose some neighbor of x1 and extend the path to that neighbor. So this would be x2. Now, the complication that arises with this approach is that we always have to find some vertex in the neighborhood of the vertex we're currently located at that isn't yet in the path. For example, when we're starting at x0, then the neighborhood of x0 needs to contain at least one vertex. Otherwise, we can't even get started extending the path. Thus, if we have a neighbor of x0, say x1, then we can get a path of at least length 1. If we now further want to extend our path from x1 onwards, then we need the neighborhood of x1 to contain some vertex other than x0. This is because paths aren't allowed to intersect themselves, so we're not allowed to repeat vertices. Thus, in this case, we can only extend the path if we have some distinct x2 that we've not already used in our path before. Therefore, as long as these conditions are fulfilled, we can extend the path further, and at some point we'll reach a vertex whose neighborhood only contains vertices we've already had in the path that we've constructed, and then at that point we have to stop extending the path. One way we could ensure that we get a path of a desired length would be to ensure that each vertex in G has many neighbors. For example, if we knew that each vertex in our graph G has at least 3 neighbors, and this translates to each vertex having degree at least 3, or in other words, the minimum degree of G is larger or equal than 3, then we could be sure that x0 has at least one neighbor, so we could extend the path to x1 from x0. Next, if we look at the neighborhood of x1, then we know that there are at least 3 vertices present in that neighborhood, and only one of those can be x0, so there has to be at least 2 distinct vertices in the neighborhood that aren't x0, and we can then extend the path to one of those, which we would call x2. And finally, if we look at the neighborhood of x2, we again know that this contains at least 3 vertices, and at most 2 of those could be either x0 or x1. So there has to be another vertex which is distinct from x0 and x1, which we'll call x3, and we can then further extend the path to that vertex x3. At this point, if the minimum degree of G is 3, then we're not guaranteed to be able to continue, since the neighborhood of x3, we know it has to contain at least 3 vertices, but these 3 vertices could be precisely the first 3 vertices that we've used in our path. So the neighborhood of x3 could contain x0, x1, and x2. And now we can no longer extend the path because if we were to add another edge to the path, we would get an intersection. Thus, in this example, we've seen that if we assume that the minimum degree of G is 3, then we can find a path in G which has length 3. We generalize this result in the following proposition. It states that every graph G contains a path of length at least delta G. Furthermore, if delta G is greater or equals than 2, then G contains a cycle of length delta G plus 1. We could prove this statement using induction with exactly the same idea that we used in the example before. However, the proof I'm going to present uses maximality, and this allows us to get straight to the case we're actually interested in, which is the case where we've extended the path as far as possible and we are no longer able to extend it any further. We do this in the following way. We let P, which is some sequence of vertices x0 through xk, be the longest path in G. Thus, in this case, P is our maximal object. And we know that a longest path must exist because we're only looking at finite graphs G, and therefore there's only a finite number of paths in G, and one of those has to have the longest length. Okay, so we have this path P, which goes from x0 to some other vertices. We might not know how many, and then it ends at xk. We can now ask ourselves what we know about P. At first glance, it may seem like we don't know very much. However, the fact that P is the longest path in G gives us a lot of leverage. To see this, suppose that U is some other vertex in G. Now assume that U is adjacent to xk. If U wasn't already a part of the path P, then we would be able to make a longer path by adding the edge xku to our existing path P. But this is impossible since P is the longest path in G. Therefore, we conclude that U must lie on the path already. Otherwise, we would be able to extend it further, which is a contradiction. So in fact, the picture I've drawn this way is misleading. The real situation is as follows, namely that U lies on the path P, and that the edge xku goes like this. Now, the same argument holds for any other vertex that is adjacent to xk. For example, if we have some other vertex v, then if it is adjacent to xk, it needs to lie on the path. Therefore, we have that the neighborhood of xk is a subset of the vertices of P without xk. The fact that the neighborhood of xk is a subset of the vertices of P follows from the previous argument, and the fact that it's also a subset of the vertices of P without xk follows from the fact that xk isn't part of the neighborhood of xk. Furthermore, we know that the neighborhood of xk contains at least delta G elements. This is because each vertex in G has at least degree delta G, and this means that it has at least delta G neighbors. Together, the above implies that the cardinality of the vertex set of P without the element xk is at most the cardinality of the neighborhood of xk, because the latter is a subset of the former. And we know that this is at most delta G. Therefore, we have that the cardinality of the vertex set of P, which is equal to the cardinality of the vertex set of P without K plus 1, because we know that xk is an element of the vertex set of P. And we know from the above equality that this is greater than the cardinality of the neighborhood of xk, and we still have that plus 1 hanging around, which is greater or equal than delta G plus 1. Thus, we've now shown that the vertex set of P has at least delta G plus 1 elements. This shows that the length of P is at least delta G, because a path on n vertices has length n minus 1. With this, we've shown the first part of the proposition, and we now turn to the second part, which claims that G also has a cycle of length delta G plus 1. For this, we again consider the longest path P, and as before, we look at the neighbors of the vertex xk, which we know have to lie on P. We now look at the neighbor of xk that has the smallest index. So that's the neighbor of xk that's on the furthest to the left. Now, another way of saying this is that all neighbors of xk lie to the right of this neighbor with the lowest index. Thus, in the section of the path between the neighbor of lowest index, which I've indicated in green, and xk, we have at least the cardinality of the neighborhood of xk minus 1 vertices. If we call the neighbor of lowest index xi, we can look at the path that goes from xi along P to xk. This is the path that I'm now drawing in red. We know that this path has at least the cardinality of the neighborhood of xk minus 1 internal vertices, and then we have the two additional vertices, xi and xk. So the cardinality of the vertices of this path is at least the neighborhood of xk minus 1 plus 2, which is equal to the cardinality of the neighborhood of xk plus 1. And we know that the cardinality of the neighborhood of xk is at least delta G. So we get that this quantity is greater or equal than delta G plus 1. This shows that the path xi p xk has length at least delta G, which implies that the cycle, which we obtain by adding the edge xi xk to this path, so that's xi p xk union xi xk, has length at least delta G plus 1. This is because we've added an additional edge to the path from before. And with that, we've shown the proposition. That's all for today. Next time, we'll continue looking at paths and cycles.